This one's going to be, let's enlarge this. So it's going to be 5-6, which is Hess's law. And this one, I think you're going to get. It's really not too bad. It takes a little while at first to get it, but really it's just remembering some of those things that we talked about with delta H the other day, and I reminded you of one of those right before we took the test, and that is if I have an equation like H2 plus O2 yields H2O, and this isn't balanced, but I'm just trying to do this quickly here, and let's say I've got a delta H for that reaction, okay, whatever it is, then if I flip the equation around, H2O yields H2 plus O2, so it's breaking apart now. The delta H is going to be equal in magnitude but opposite in sign, right? So basically you just flip the sign on the number on delta H, okay? So that's one of the things we got to think about here. Now, turns out because this is a what's called a state function, and you don't really need to know what that means necessarily for the AP exam, but I'll give you just a very quick background here. A state function, it's not the journey that matters, it's the destination. So it's like the opposite of Miley Cyrus's The Climb, if you will, okay? I'm going to reference that. It's not the climb, it's that you get there, all right? That's what matters. So an example of this, let's say that you go from St. Louis and you drive to Denver, Colorado, okay? Elevation in St. Louis is about 455 feet above sea level. I know this because of the radiation thing that I gave you guys last year. You guys remember that, where you had to fill out your own personal radiation dosage in a year or whatever? It tells the elevation of St. Louis on there. So about 455 feet above sea level. The elevation, do we know the elevation at in Denver?
Higher.
Called the Mile High City, so probably around the mile high. Does that make sense? All right? Yeah, 5,280 feet or so. So, does it matter which way you get to Denver as far as your overall elevation change? If you're going from St. Louis to Denver, your elevation change is going to be 5,280 minus 455, right? Regardless of which path you take. You can go through Canada if you want to and come back down, but your overall elevation change is going to be the same, right? That's a state function. It doesn't matter what path you take, it just matters the start and the end are what matter, okay? So that's kind of the idea here. And because delta H is a state function, doesn't matter what path you take to get there, you could perform a series of reactions. But if the overall result is that you have H2 plus O2 giving you H2O, then your delta H for that series of reactions would be exactly the same as your delta H for this one. Okay. So there's a couple other things that you can say because of that. One of those is if you double the coefficients here, this is also an extrinsic property, delta H is, okay, which means that if you double the amounts, you're also going to double the heat produced, okay? So multiply this whole thing by 2. Now you have 2H2 plus 2O2 yields 2H2O. Again, this isn't balanced, so just bear with me here, okay? That's going to be 2 times the delta H, all right? So you multiply the equation by 2, you have to multiply the delta H by 2, all right? But it also means, let's say that I've got a couple of reactions, and I add those reactions together, like maybe the reactions happen in a series of steps, and the example they give in the book for this is you've got something like CH4, the combustion of CH4, okay? Plus 2O2 yields CO2 plus H2O. See how that balances. Just 2 in front of the H2O. So then your delta H for that one is negative 802 kilojoules. And then let's say we have a separate reaction. of H2O gas, and this isn't really a reaction per se, but H2O gas going to H2O liquid. And I should have included the state of matter on this top one. H2O gas here, okay? So then the gas goes to a liquid. That'll be a 2 as well. And the delta H for that process is negative 88 kilojoules. Then I could actually add these two equations together. All right? And if I add them together, then my net equation, my overall equation here, I would actually end up with CH4 plus 2O2 yields CO2 plus H2O liquid. Now what happened here when I added these two together, I've got H2Os on this gas, H2O on this side, gas H2O on this side, so they essentially cancel each other out. Kind of like in a system of equations in algebra. Cooled, okay, and turned into a liquid. So if I add these two equations together, then I can just add the delta H's together, and that gives me the delta H for this overall new reaction that I just performed, okay? So that's going to end up giving me a negative 890 kilojoules, okay? And that's basically Hess's law. If you add equations together, add up the delta H's for those equations, and the total reaction should have the delta H of the total of the original delta H's. Okay? So you add up the equations, make sure you add up the delta H's too. Now why in the world would that ever be useful? I mean, it's kind of a cool thing that we can do, but why would we ever need to know that? Thoughts? Okay, so maybe for if we think we've got a series of reactions happening here, could possibly be for that. Okay. Another reason is if you've got a reaction that doesn't typically happen, or we have trouble getting it to happen, but maybe theoretically we just want to know how much heat should be produced in that reaction if it occurred. Trying to think of a good example of this. Okay, actually the practice exercise on page 187 is maybe a good example. So you want to know the heat change associated with graphite turning into a diamond. Okay, so let's go over this example because I think this kind of shows where this can come in handy sometimes. Not that that really, in any practical sense, really matters, but let's say that we just want to know that. Okay, so we know these two equations. We know that the carbon as graphite excuse me, if that combusts, and that's going to give us CO2, right? The delta H for that process is negative 393.5 kilojoules. Okay. Oops, diamond. So carbon is diamond. If we burn that, it's a little weird, but diamond will burn. Will also give you CO2. And the delta H for that process is negative 395.4. Let me erase this part because that's not part of what we're looking at right now. Okay, so let's say that we want to know the heat change associated with a carbon as graphite turning into diamond. Now, does this happen naturally? Does graphite turn into diamond naturally? Well, it depends on how long a period of time we're talking about, right? And how much pressure it's being put under and how much heat there is, right? But yeah, this actually can happen. That's where diamond comes from, right? Is this incredible amount of pressure that's put on graphite, this form of carbon, that turns it into a diamond, okay? So this will happen naturally. It takes a really long time for it to happen. But we're just interested in the heat change associated with it, the overall heat that is either gained or lost in this process, okay? So what I need to do is figure out a way to add up these two equations so that they look like the last one on the example, C graphite to C diamond. You guys see that? So how would I need to change these equations in order to make them look like, when I add them together, make them look like that final equation? Yeah, I need to reverse one of them, and which one would I need to reverse? Okay, the bottom one, the one with the diamond, because that diamond needs to be on the product side, right? So we'll reverse this, okay? We'll write it backwards here. So we've got CO2 gas yielding O2 gas plus C in diamond form. Now when I do that, I have to change something else, don't I? What else do I have to change? Yeah, I have to change the sign of my delta H. This is now a positive. Well, that doesn't look like a plus sign. And that doesn't look like anything. It is now a positive 395.4 kilojoules. Okay? So now, when I add these two things together, carbon dioxide cancels out. The oxygens cancel out. The arrows are kind of in different places, so that's hard to see. But so then you end up with just graphite going to diamond. And the delta H for this process ends up being what? That's right. 1.9 kilojoules. Interesting. It takes 1.9 kilojoules of heat to change graphite into a diamond. Why don't we do that more often? It seems like that would be really easy in theory, right? Well, technically it also takes an enormous amount of pressure, right? This is just the heat change that's associated with it, okay? And so we haven't even talked about something called entropy yet. Things like to go towards more disorder, not more order. Diamond is much more orderly than graphite in its arrangement. So to get it to put itself in order in that way, you really have to work against the grain of the universe. So it's a little bit harder than it seems right here. It's not just a matter of adding 1.9 kilojoules of heat energy to it. So that's why if we don't do it more often. Yes, ma'am? It's because they're on different sides, because we're sort of doing like a net reaction here, right? So if you've got two things that are exactly the same on both sides of the equation, when you add them together, just cancel them out. It might be easier, actually, for you to see it if I just go ahead and add everything together, right? So we've got the graphite. I'm going to abbreviate a little bit here so I have room. Plus my O2. Those are my reactants from the top equation, right? Plus the CO2 from the bottom equation yields CO2 in the bottom equation. Sorry, top equation, sorry. Plus O2 from the bottom equation. See, I'm running out of room. Plus the diamond from the bottom equation, right? And so, I'm sorry, yeah, I know that's really weird looking. But here's our arrow, right? If I've got O2 gas on one side and O2 gas on the other side, and we're thinking about our net equation here, well, let's just get rid of those. Okay, same thing with the CO2s. So then you end up with just this net reaction of the graphite turning into diamond. Okay? All right, so that's kind of the idea behind Hess's law. There's not a lot else to it that I think we need to really talk about. There's a lot of good practice problems in the sample exercises, and then I'll give you quite a few practice problems on this when we're in class tomorrow. We may not get to do them all in class, but I'll give you a worksheet that has several of them so that you can practice some of these. But that's essentially what you're doing, is you're basically just rearranging these equations, and you got to remember 3 basic rules. If you flip an equation, change the sign. If you double the whole equation, if you have to multiply the whole equation by 2 to get it to work out, then multiply the delta H by 2, okay? And then when you add the equations together, add the delta H's together. Really, that can kind of be summed up in one rule. Whatever you do to the equation, do the same thing to the delta H, right? A good example of that would be like sample exercise 5.9 on page 187. So rather than working that one all the way out, I'll just let you kind of take a look at it. On that one, we need to end up with 2 carbons on the reactant side. So the top equation they show you here, the 2 carbon plus H2 yields C2H2. That's the equation we're trying to get to. And we're trying to add these other 3 equations together in order to make that top equation. All right? So notice the middle equation here, there's only 1 solid carbon, 1 mole of solid carbon there. We need 2 in our final equation. So what they end up doing, if you look down under the solve here, they have multiplied that middle equation by 2, the whole thing, and then they multiplied the delta H by 2 as well. Okay? So there will be times when, in order to get to what you need at the end of the problem, you would have to multiply the whole thing by 2. Okay? Or sometimes in order to get something to cancel out the way that it needs to, you'd have to multiply by 2. Okay? I mean, that's the basic idea of Hess's law. So other than that, it's just, a lot of practicing with these things. But I think traditionally students have liked Hess's law and haven't had too much trouble with it. It's very algebraic, And so you're kind of doing the same thing as you would do with x's and y's in algebra. All right. I think we're good. We'll see you guys in class tomorrow.